Welcome back, students. So let us continue the previous topic in our part 2 video. Here we are considering a conductor. Why we are taking it in a cylinder form? I have shown you the wire. If you consider that wire and if you imagine that wire in a zoomed extended form, so what will be the shape of that wire? The shape of that wire will be something like the chalk, a cylindrical shape. The same shape we are considering to represent the conductor. And what happens in that conductor? There are electrons, they move in that particular conductor. So what we are saying, this current I is nothing but charge per time. How many charges are moving in that particular time? Suppose here I am taking some time instant, I am taking this cross sectional area, and at particular time t, if I want to check how much current is flowing in this area only, then what will give the value of that current? How many number of electrons are moving from that particular area in that given time. That is nothing but current, that is charge per time. So that is another expression of current. So first relation gives the Ohm's law. Second relation, the physical definition of current. The basic definition is charge per time. So here we have current I. Now we will compare it with the previous topic of electric field. We have discussed electric field and we have given it with Coulomb's law. That force is proportional to Q1, Q2 and inversely proportional to R square. This particular force is related with electric field, as electric field intensity is defined as force per charge. How much force we are applying on a charge for making it move. So when I say electrons are moving, when I connect them with some kind of battery. Battery have two terminals. Always there are positive and negative terminals on battery. That we will discuss in next session. Before that, we have to understand that unless we have battery, we don't get the electron. What happens when we apply battery? We get electric field. What is that electric field? It is force per charge. So we are applying force on particular charge, then he is moving. That is nothing but E, electric field. And what is current? It is charge per Q. How many charges are moving in that particular time? We apply force, we get the moment of current and we call it as I, current given in ampere. So this is second expression of current I. So 1 ampere, how we will define? What is unit of current? Unit of current is ampere. So 1 ampere will be equal to charge per time. What is unit of charge? Charge is given in coulombs. Why in coulombs? This relation of charges was given by coulombs. We have just now seen in the Coulomb's law. Unit of charge is coulomb. Unit of time is seconds. So it is coulombs per second. 1 coulomb per second. Now if I ask you how many electrons will be there in 1 ampere? This is a very tricky question. Usually we get in objective type questions or MCQs. So most of the students, they feel that okay, 1 coulomb by say 1 second, it will be 1. But it doesn't work like that. Here you have to pay your attention. 1 coulomb having a fixed value, that value is equal to 6.625 into 10 to the power 18 electrons. That means there are so many electrons in 1 coulomb. So what will be the 1 ampere current? In 1 ampere current, the density of electrons will be this value, 6.25 into 10 to the power 18 electrons. You can imagine the number of electrons. We cannot see electrons. Those are very minute objects. When I say conductor, there are millions or trillions of electrons present in that particular wire. And they constitute the current given in amperes. And now we will move to the third expression of the current in mathematical form. Now here we can see the same diagram with a cross-sectional area. We will take a reference plane, a section where electrons will be considered with some velocity. So here we will relate it with velocity. Our charge is electron, which is negative charge. So here we will consider the charge. Now we will relate it with some kind of velocity. Here we have number of electrons, say 1, 2, 3, 4, 5, n infinity or whatever is the number. So that n is, say, density of electron, number of electron. How many electrons are there? More electrons, more current. So first parameter, number of electron. If we go into the more physical appearance of the current, what we are doing? The physical appearance we are writing in a mathematical form. So here we have n number of electrons in that particular area. So we have to consider the area A. Number of electrons in that given area. How many electrons are there? What is the area? How they are distributed in the area? And what is the charge Q? Charge Q is also a fixed value. We will see in the numericals. So we have number of electrons, the area, the charge, and these are not static charges. They are not idle. What they are doing? They are moving. So there is a velocity V. We refer it as, say, Vd, that is drift velocity. So this current is combination of these four parameters. So that is current I is equal to the density of electrons, how many electrons are moving, what is the charge on electron. If it is negatively charged particle, there is a fixed value that we will see in numerical, and what is the area of conductor. Conductor area may be small or large, and what is the velocity. From here we can see what will be the velocity expression. From here we will transfer these three terms to, say, LHS. So velocity will be equal to current by NQA. We can get that value. So Vd is equal to I by NQA. If you take example of copper, copper is a wire. Usually you might have seen the value of copper. The number of electrons density in copper is 8.5 into 10 to the power 28. That is experimental value calculated, and that is a constant value for copper. So this is the copper. This copper looks like, it looks something like that, and that particular value we have to keep in the example. Then we will move to our other remaining questions. How can we decide the direction of electric current, and what is the actual and conventional direction of the current? So let us first discuss with first approach, with Nature's law. What is the Nature's law? Nature's law states that everything should follow the potential which reflects, say, higher to lower value. If you talk about the flow, what happens? The flow, whenever we pour some water, if you see the river or anything which flows, it flows from the higher level to lower level. So what Nature's law say that everything should flow from higher level to lower level. But electrons do not follow this particular formula. They flow from the negative terminal to positive terminal. Why? Electrons are negatively charged particles. So what is their basic behavior? We have seen in the behavior of charges, the opposites attract. So negative charge particle will get attracted toward the positive terminal. They get generated at negative terminal and they try to go toward the positive terminal of the battery or voltage source. So they are moving from lower potential to higher potential. That is also called as the actual direction of current. But for mathematical purpose, we consider conventional direction of current, which considers the Nature's law that everything should flow from positive to negative. So when you will solve the mathematics about the wires and the elements, then you will use the direction as positive to negative. But what is the actual direction? Actual direction is from negative to positive. To understand this, we can have another approach also by using the equation what we have discussed. What is the sign of charge? It is negative. Our expression for what happens with the current is that number of charges moves. Number of charges N, Q. They move in particular area A with some velocity V. So if we talk about a conductor where electron is the charge, so electron is negatively charged particle, so we get negative charge. So current flows in the opposite direction to the supply voltage. So who can decide the direction of electric current? So the charge, the polarity of the charge can also decide the direction of the current. If in any case we consider the positive charge, then the direction will be from positive to negative, because positive charges will get attracted towards negative terminal. This is a very important concept. Everyone should remember this. So this is about the actual and conventional direction of currents. So let us move to the next part. So here you can have the second question. This question will be not given in the form directly. You have to take it from here and you have to answer. The question is, what is the amount of current flowing through an electric press, the iron, if the amount of charge passing through a conductor is 10 minutes in 300 coulombs? So you have to take care of the values, how to convert it into seconds and all. And you have 4 options for this. The 4 options are, say 30 ampere, 0.3 ampere, 0.5 ampere or 5 ampere. This you have to answer there. So now let us have a live demonstration about the batteries, LEDs, resistors and wires. Then we will move to next part. So if I show you the battery may have a different voltage. So battery, if we consider some 9-volt batteries, these batteries, if we open, there are various small batteries connected together in series, say 1.5, 1.5, 1.5, 1.5, 1.5, total 9 volt. If we open this particular cell size battery, there are also various combination of small button batteries connected together in series, and every battery have a different voltage level. Together they make some 9 volt or 12 volt according to the battery. Inside the cars and all, we have batteries. At home we get supply from the electricity board. So these things we will demonstrate. So let us have a look at the demonstration. Okay, due to some space problem, we will continue this video in the next part. Probably we will upload it tomorrow. The demonstrations you can see in the next part. Then till then, have a good day.